Let G be a group of order 7 and phi x defined as x raised to the power 4 and x is coming from group, then phi is not 1 1, not on 2, not a homomorphism, and option D is 1 1 on 2 and homomorphism. In this question, we have to test three things: 1 1, on 2, and homomorphism. You can check all four options, and these all four options about 1 1 on 2 and homomorphism. Given condition is G is a group and order of G is 7 and 7 is a prime number, and we know that a group of prime order is always cyclic. This is a theorem, cyclic, and every cyclic group is abelian. Indirectly, property of commutative group is given. We need to check 1 1 on 2 and homomorphism. First, what is the information given? As G is cyclic and order of G is 7. Because G is cyclic, it is generated by, suppose, X. So order of G will equal to order of its generator, and generator gives x raised to the power 7 equal to E. This is the property of generator. And this is least positive integral power when we get E. As phi is given, phi x, the rule for phi is given x raised to the power 4 for all x is coming from G. And suppose here this x is group element and this is generator, so you can change generator as A, avoid confusion. So phi A will be A raised to the power 4 as expression of phi is given. Phi of A square, as this is input, and how phi gives output. Input raised to the power 4. Input is A square. Input is A square. So A square raised to the power 4 gives A raised to the power 8, and it can be written as A raised to the power 7 into A, and this is nothing but E. So this is A. Means A square is A. Now phi A cube will be A cube raised to the power 4, means A raised to the power 12, means A raised to the power 7 into A raised to the power 5, and this is E, so A raised to the power 5. Phi A raised to the power 4 will be A raised to the power 4 raised to the power 4 by defining nature of phi. It will be A raised to the power 16, and it can be written as A raised to the power 7 into 7 into 2, so A square. Phi of A raised to the power 5 can be written as A raised to the power 5 raised to the power 4, and this is A raised to the power 20, and it can be written as A raised to the power 7, 7 and 6. So A raised to the power 6. And last one is phi of A raised to the power 6 will be A raised to the power 6 raised to the power 4, and it can be written as A raised to the power 24. So 7, 7, 7 into A raised to the power 3. And you can check phi A raised to the power 7. So A raised to the power 7 raised to the power 4 it will be a raised to the power 28, and you can write a raised to the power 7, 7, 7 and 7. And this is E, 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 E. So all element of degree higher than 6 will repeat here. So you can check as you put input, you will get output for phi, output, and each output there exists a domain elements or input. For each output there exists a input, and these inputs are coming from G, group G. So phi is onto, and clearly for each input, there is distinct output. So phi is also 1 1, phi is 1 1. Now here we got 2 points about phi is 1 1 and onto. Now we have to check onto property. As G is cyclic and order of G is 7, because 7 is prime and every prime order group is cyclic and every cyclic group is abelian. If two elements xy is coming from G, then xy will come to or will go to G by closure. If this is an element, apply phi, and by the property of phi, input raised to the power 4, and because G is abelian, so a b raised to the power n can be written as a raised to the power n b raised to the power n when a b are elements of G. So it can be written as x raised to the power 4, y raised to the power 4, and x raised to the power 4 means phi x into this is phi y. That is, phi of xy can be written as phi x, phi y. So phi is homomorphism and these are arbitrary element. So all first three options discard. So correct options is the number of group homomorphism from the cyclic group Z4 to the cyclic group Z7 is. In general, given information is cyclic group over cyclic group Zn, and this group is cyclic as well as abelian with respect to operation addition modulo n. Now the number of group homomorphism from the cyclic group Z4, suppose this is a function from Z4 to Z7, the number of group homomorphism can be easily find out by GCD of, if this is M or N, then we can in general find the number of group homomorphism by GCD of Mn. This will give you number of group homomorphism. As this question is particularly asked about Z4 to Z7, then number of group homomorphism is by GCD of 4 and 7, and this is 1. So option D is right choice. How many elements of the group Z50 have order 10? To solve this problem, first we have to recall some facts about related terminology you can use in these types of problem. How to find
order of an element in the cyclic group. This is our first motive. Properties of Zn, integer modulo n. Actually, these two are same. And Z50. Z50 is cyclic group. You can say it is integer modulo 50 group with respect to addition. We have to find order 10 elements, number of elements of order 10, because 10 divides 50. So number of element you can find with the help of Euler 5 function. Number of element of specific order d in Zn you can easily find. If d divides n, the number of element will be phi d. If d doesn't divide n, the number of element of order d is 0. With the help of this concept, you can evaluate the value of Euler 5 function 10, and value of this one is 4. How you will how will you get 4? 10 equals to 2 into 5. So you can use these factors as 1 minus 1 upon something. Similarly, after solving this, you will get 4. So option C is right one.
Let P be a prime number. The order of a silo P subgroup of the group GL50FP of invertible 50 by 50 matrices with the entries from the finite field FP equals. Means we have to find the order of the silo P subgroup. Order of silo P subgroup. In general, either GLN FQ or SLN FQ, general linear group or special linear group, and entries are coming from the finite field FQ. Then G has Q silo subgroup of order Q raised to the power n into n minus 1 divided by 2. For this problem, P is used instead of Q and n is 50. So order is P raised to the power n minus 1 divided by 2 by this structure or formula, and value of n is 50. So P raised to the power 50, and 50 minus 1 49 divided by 2. 2 cancel out 50 25 times, and 25 49. 25 into 49. This is the exponent of P, and this exponent will give you P raised to the power 1225. So option D is right. The order of the group Z over 30Z is, we have to find order of this group. We know that for each prime, for each not a prime, it is true for natural number, Z over Nz is isomorphic to Zn. This is the result, or you can say as a theorem. So Z over 30Z is isomorphic to Z30, and we know that order of this is 30 because two isomorphic group have same order. So order of this one will be the order of this. So true answer is option D.